Well, I found in this class that there's all these like little loose topics that we really need to cover somewhere, and they don't kind of fit in other topics. So here they are. Okay, this is just sort of background information, good things to know, but don't fit into some of the other notes. So here we go. Okay, so 3 reasons to study parallel programming. And as you are so cool for being here, why do we care? One, parallel programming lets you do more work in the same amount of time. You want to increase performance. You want to increase the size of your problem that you're trying to solve, but not have it take any longer to run. All right, parallel programming is a good thing. Or number two, increase performance. You want to do the same amount of work, but you want it to take less time. A lot of things in game programming are like this. So, yes, parallel programming to the rescue. And number three is make some programming tasks more convenient to implement. The great example is a web browser. You download a link and a whole bunch of things are happening at the same time. Multiple pictures are coming across and equations are being turned into pixels and tables are being formatted and all of that. And web browsers are very paralleled, very multi-cored because they have to be doing these things simultaneously. If it takes a long time for one image to get downloaded, because of the server it's on, you don't want that stopping the entire page. You want it to go ahead and be downloading other things. So yes, this is a good example of why we're here in the first place. All right, there's 2 kinds of parallelism we're going to look at. One is called data level parallelism, and that's what we're probably going to look at the most. But it's the idea of same instructions get operate on different data. Okay, so if I had a for loop like this, I could break it up into the first third, the middle third, and the last third. Same equation, but different parts of the data. And of course, we're going to talk a lot about this. The other kinds of parallelism that we will look at is something called task level parallelism or functional parallelism, and it's executing different instructions. Okay, so you've got some amount of things going on. And this is sort of the idea of the web browser again, is it's got many things it's doing simultaneously to get a certain web page to load. Well, let's just put them all on different threads. And so that's functional. And you'll do an assignment. You'll do a programming assignment doing functional parallelism like that. Okay, sort of while we're on the topic, there is something called Flynn's taxonomy, and it's a 2 by 2 grid. The amount of data goes this way. Now, SD stands for single data, MD stands for multiple data. And this is the idea. So OSI stands for single instruction. So single instruction, single data, that's sort of normal computing. Y equals AX plus, or Z equals AX plus BY. One equation, one set of numbers, compute the result. SIMD, which is how that's pronounced, is single instruction, multiple data, and we'll get to that, where we have one instruction, but it can do multiple operations at the same time. So if you have 2 arrays of floating point numbers, you can multiply them 4 pairs at a time, or 8 or 16, depending on what kind of SIMD you have. MIMD, the M stands for multiple instructions, multiple data. This is sort of like the functional programming, is it's multiple processors, multiple cores running independently but simultaneously. And in theory, there should be a MISD, multiple instruction, single data. And I'm not aware of anything that we'll encounter here that does that. I have heard of this in fault tolerant systems where you have one set of data and you have multiple processors compute the same result just to make sure you're getting the same result. But No, we're not going to talk about that. But this is worth knowing. And I've heard from students that oftentimes they get asked this on job interviews. Hey, explain Flynn's taxonomy. So for that reason alone, it might be worth knowing. Okay, von Neumann architecture. This was developed by John von Neumann um, in the 50s and 60s. And really, these are the fundamental pieces that haven't changed. They've just gotten bigger and better and faster. So here we have memory. This is the heap, which is, if you do a malloc or a new, that memory gets allocated here. The globals are here and the stack is here. There's an arithmetic logic unit. Well, now we have, well, then they had one accumulator. Now we have gobs of registers. But here's where the arithmetic takes place. Add, subtract, multiply, divide, shifting, all kinds of stuff. And the control unit has to do with flow control, go-tos, for loops, while loops, and so on. And they all work together. Now, there are other elements that will be really important to our discussion of using parallel programming. One is the clock. The clock goes tick, 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 and every tick, things fly around this network. The registers, which is like the accumulator, only a lot more of them. The program counter, which is a memory address pointing to where is the next instruction going to come from when we're ready for it. And the stack pointer. You use a stack for local variable storage. You use a stack to handle arguments to functions and to handle the return address from the function. Yeah, so these three things together are referred to as the state. And this is what lets us do multi-threaded programming. Multi-threaded programming it's the same program, the same code, occupying the same memory, except each thread is executing in a different place in it. And that thread state tells it what to do. So when you have to swap between threads, yes, you swap out all of this and you swap in the next thread's state. Yeah, we're going to see this a lot more. All right, so what exactly is a process in a computer? You've got a sense of this if you've taken OS1, but it processes execute a program, and the process keeps the state. It knows what the values in the registers are. It knows where the program counter is pointing, where's the next instruction coming from, and it knows where the stack pointer is, local variables, arguments to functions, and so on. Okay, so what if we include more than one set of these? Now we have threads. Okay, the program and the data in memory are all shared among these threads. The threads are executing the same program, just not in the same place necessarily. Is one of them, one thread may be executing code up here for some reasons, another thread may be executing code down there. But it can do that because each thread has a different program counter. So when that thread gets swapped in, the program counter tells it where to pick up in the program, which is common to each. When a thread gets swapped in, it also brings in its registers, which were the value they were when it got swapped out. And it also brings in the stack pointer so that that thread knows how to find things like its local variables and arguments to functions. In a single threaded program, this is typically, well, this is one way that they allocate memory. And don't take this completely literally. Some operating systems do it differently, but the idea is still the same. We have a program executable. This is your machine code. We have global variables, which you've declared ahead of time. And we have the heap, which you've created at runtime. Every time you say malloc in C or new in C++, you create more data storage here. And then we've got the stack. And as the stack grows, it moves in a certain direction. Now, in a multi-threaded program, let's see what's the same and let's see what's different. The program executable is the same. Okay, all threads are executing the same machine code. just at different places. The globals are the same. Okay, when you write your code and you create globals and maybe put values in them, all threads get to look at it. Okay, the heap. If one thread says malloc, well, all the threads have access to that. Okay, as long as they can get at the address somehow. But that's in common. What's not in common is the stack. Each thread has its own stack because each thread is going to be creating its own unique local variables, its own arguments to functions, and so on. So really, nothing changes in a multi-threaded world except for having multi-stacks. Okay, and so that's really what a thread is. It's an independent path through the program code. And it's the same program code among all threads, but they potentially are executing it in different places. All right, where's it good to do this? Well, sometimes operations can become blocked. Like if a web browser is trying to download an image from a very slow web server, well, that's blocked, but now because everything else is on different threads, they can go off and keep running. So that's a good thing. When certain operations are CPU intensive, well, you don't want them blocking what else is going on in the program just because this one is going to run for a long time. It's going to take a long time. So that's a good use for multi-threading. Sometimes when certain operations need to respond to asynchronous I/O, like, oh, that image from that slow web browser is finally there. Okay, that's good. Um, Independent behaviors. This is like the functional programming, the task programming, where you have different things going on in the code, and that's fine because there's different threads in charge of each one. Or when you want to accelerate a single program with multi-core CPUs, and that'll be really important. Threading existed before there were multi-core chips. Okay, and it was still useful for all the reasons listed here, except the last one. But once there were multi-core CPU chips, now the threading really made sense because that was the only way you could get at the multi-core parallel processing. All right, here are some definitions. Again, these are loose topics, not sure where to put them. Atomic means an operation that takes place to completion without any chance of being interrupted. Okay, and we're going to see this if you go look at the trapezoid program notes. You'll see a great example of that. Barrier is a point in the program where all threads must reach before any of them are allowed to proceed. Think of it as a gate. You shut the gate, all threads have to get there before the gate's allowed to open. This is if the next thing that's going to happen in the program needs the results from the parallel computation. You don't want any thread going forward until all the results have been computed. Coarse-grained parallelism is a term that means you break up a task into a small number of large things. Fine-grained parallelism down here is breaking a task up into lots of small things. Deterministic, that means the same set of inputs always gives the same outputs. Multi-core programming is not deterministic. Okay, you have no control or even no knowledge of the scheduling. Dynamic scheduling means taking the total number of things that you're trying to do, like maybe they're for loop iterations. um, and so you divide that up so that each of the available threads doesn't have exactly T over N subtasks to do. You make that so they each have less. And then the first one to finish gets to attack the remaining list. Okay, this is in contrast to static scheduling, where you divide up the tasks exactly evenly. Well, but that means if one of them finishes early because of the nature of the tasks, well, it has nothing to work on while all the others are doing the work. And so dynamic scheduling is a way to kind of recover some of those idle cycles. A shared variable is a variable that gets shared among all the threads. If one thread writes it They all see that changed value. A private variable is a variable that, well, is local to each thread. Okay, if one thread writes to it, the other threads don't get to see it because they've got their own copy. Reduction means combining results from multiple threads into a single sum. Yeah, you'll see this in the trapezoid notes. If you go, well, you will, of course you will go look at it. Okay, speed up, the time it takes to execute with one thread divided by the time it takes to execute with n threads. If you go from one thread to four threads, the four thread one should run a lot faster, maybe even 4 times faster, probably not. But that ratio is known as the speed up. Speed up efficiency is the speed up you get with n going from 1 to n divided by n. And we would love to have a speed up efficiency of 100%, but your experience with perpetual motion machines probably says, no, we're not going to get to 100%. All right, I threw some parallel programming tips in here for you. Tip number 1, don't keep internal state. Now, ironically, a whole lot of the Linux standard functions were written with internal state because when they were first developed, there were no multi-threaded machines. And so this was safe. Stirtoke is the perfect example. What Stirtoke does is it breaks up a string into the tokens. And when you do this, you give it the name of the string and the delimiters, what will separate the tokens, usually tabs and blanks. And it gives you back the pointer to the first token. And then from then on, you keep calling it and it gives you back a pointer to the next token. But notice nowhere in here do you tell it where to go. Like here, we told it to go to the start of a character string called line 1, but we're not telling it that. How does it know? It knows because it's keeping that pointer internally. Well, okay. So here was what can happen. Here's why you don't want to do that in a multi-threaded world is, okay, we do this, we execute this code, and now the internals of stirtoke have a pointer to the next token on line 1. But threads get swapped, and now thread 2 is calling stirtoke with a different overall character string. That changes the internal state character pointer. Scheduler swaps them again, and now thread 1 is doing this, but that internal pointer is pointing into thread number 2's string, not the string thread 1. And so amazingly enough, what this would do is it would produce tokens for thread 1 that thread 1's string didn't have in it. This is why you don't want to do it. Okay. There is a stirtoke R, at least on Windows. The R stands for reentrant, meaning multiple threads can enter that function with no damage, with no possible side effects. Okay, so if you have a choice, you do stirtoke R. Okay, and stirtoke R works like this. It gives you back the pointer. The pointer is not internal. It gives it back to you, and then you give it back to it. And so thread 2, it tells thread 2, where did the pointer leave off? And then thread 2 gives it back when it calls stirtoke again, or stirtoke R. Sorry, these should be R. Okay. And some people say, oh, okay, I just won't keep it inside the function. Bah. Doesn't help. If you keep global state, like just a global variable instead of inside, it's exactly the same effect. And really, doing a static variable inside a function is essentially making a global out of it. All right, tip number 2, avoid deadlock. Deadlock is when 2 threads are waiting for the other one to do something. Okay, this one is blocked. waiting for that one to do something, but this one is blocked waiting for the first one to do something. That's known as deadlock. And this is not deterministic, at least not usually, meaning you may run this code for minutes, hours, days, weeks, months, and all of a sudden, one special sequence in the scheduler, doop, they block each other. So, this is not a good thing. 3, avoid race conditions. It's called a race condition because it matters which thread gets to some part of the code or some operation first, which could be different depending on the idiosyncrasies of the scheduler. Okay, a perfect example is pushing and popping from a stack. Okay, thread 1 does the push, and this is the code for doing a push, and this is the code for doing a pop. Thread 1 does a push, but before it can complete it, because it's got to complete both of these pieces of code, before it can complete it, the scheduler comes in, swaps out thread 1, swaps in thread 2. So now thread 2 is using a p value, or it's using data that was only partially completed. This operation was not completed. It incremented the pointer, but it didn't get around to putting data into it. So now when this tries to pop, it's going to pop the wrong number. Okay. Now, and we're going to talk about this, but this is, you solve this with mutual exclusion locks that have the funny name mutex. But you just got to know that this is a possibility. You put a mutex lock around this code. We're going to label this A. And so when your code encounters this mutex lock, it looks around and says, has anybody already locked mutex A? If so, I'm going to wait till they unlock it. If they haven't, then I'm going to grab it and lock it up. So let's say this code comes, it sets the lock because no one else has it. It finishes this operation, and then right here it frees up the lock. Thread 2 comes along, and maybe thread 1 is still executing the push code, so it blocks right here, waiting for the lock to become available. Okay, once it is, now it can execute these 2 lines of code without any chance of interruption. Volatile keyword. Before threading, we never had to worry about this. If I wrote code that looked like this, int val equals 0, and then a little while later, I followed it up. Yeah, while val is not 0, keep looping. Well, that would drop out right away. And so a good compiler will just take that code right out of there because it knows val is 0. And along come threads, which can change values of global variables in the background. So what you do is instead of just int val, you say volatile, and that tells the compiler do not do any optimizations of this one statement. Okay, assume nothing. And in many instances, that's important. There's a note set called a tale of 2 assembly codes. Be sure you look at that. That's a good example of where volatile was needed. And I didn't do it. And so, boom, program just deadlocked. Okay, when we get to caching, we're going to talk about something called false sharing. And false sharing gives you performance like this. Like so the blue line here is the speed with 1 thread. The red line is the speed with 2 threads. And look, I add more threads and the performance drops. I add 4 threads and the performance drops even more. Yes, this is a mystery, and we will come to that when we get to the caching notes. Okay, so there are some gotchas in the parallel programming world, things to watch out for, and just some general programming tips.